Hi, I want to talk about how resistors behave when they're subject to an alternating potential difference source rather than a constant potential difference source like a battery. Now, the short answer is Kirchhoff's rules apply in all situations. So any gain in potential difference you get going around a loop has to match the loss in potential difference that you see going through that loop. So with the case of a resistor, if I have a potential difference from a power source that's equal to a maximum times an oscillating component, say the sine of omega t plus some phase angle phi, well, the voltage from my source would have to be equal to the current in my circuit times my resistance. So my current is just going to be the maximum voltage over my resistance times the exact same trig function, the sine of omega t plus some phase angle, which Vmax over R would just be my maximum current. Now, if you were to average V as a function of time over one cycle, or average I as a function of time over one cycle, you're going to get a factor of 0, because the sine is a completely symmetric function. However, if you want to talk about power being delivered, you're actually going to end up delivering some net power to that resistor per cycle. So power is going to be a function of time. And the power delivered as a function of time is the current as a function of time times the voltage as a function of time, which is also current squared times resistance, or voltage squared over resistance. So if I multiply my current and my voltage together, I get my maximum current times my maximum voltage times the sine squared of my oscillating term, the frequency omega times time plus any phase angle. Or I could have my maximum current squared times the resistance, same oscillating function, maximum voltage squared over my resistance, same oscillating function. And the sine squared is symmetric, but not around 0. It's always going to be a positive value. So anytime the voltage is greater than 0, there's going to be some power being delivered to that resistor. And if you average the sine squared over one cycle, you end up with a value of 1/2. So the average power delivered would be 1/2 the maximum current times the maximum voltage, or 1/2 Imax squared times the resistance, or the maximum voltage squared divided by 2 times the resistance. Now, to make AC work like DC when we have a constant current coming from a battery, we can, instead of talking about maxima, we could talk about what we call the RMS current and RMS voltage, for root mean squared. And it's a way of talking about average voltage and average current, so that you would just have to use the rules that we talked about with DC to figure out power delivered for an AC resistor. So to make a voltage times a current be the power delivered. And to do that, we use our RMS value. So what you do to calculate an RMS is you start by taking the square of a value, V squared. You then take the average, the mean, and then you take the square root of that in order to give you your average value. So the square's mean, we said, is 1/2, so the square root of 1/2 gives me 1 over the square root of 2. So for the RMS current, we would end up having our maximum current divided by the square root of 2. For the RMS voltage, we'd have our maximum voltage divided by the square root of 2. So with household electricity, we say that the electric potential from a wall outlet is 120 volts. What we don't usually say is it's 120 volts RMS. There's actually a 169 to negative 169 volt oscillation that happens at a frequency of 60 hertz. Now, with any current that we talk about, to say a light bulb has 1/2 an amp of current in a household circuit, that would be 1/2 an amp of RMS current. Now, I try to be careful if I'm talking about RMS or if I'm talking about peak to say RMS or to say peak, but it's understood when you're dealing with AC that you're dealing with RMS values unless you're specifically told that it's peak. Or another thing that you might sometimes hear is what we call peak to peak. Now, you might think that peak to peak means from the top of a signal to the next top of a signal. Peak to peak actually means from the maximum positive to the maximum negative. So that's peak to peak, and peak to peak is twice our maximum value. So the peak to peak voltage that you would get from a household wall outlet is going to be just under 340 volts. The amplitude, or the maximum value, as I said, is about 169 volts, and the RMS value is what the power company's trying to sell to us. That would be a signal occurring at 120 volts RMS. Thanks for watching.